size as the input, where pixels have value 1 if they belong to an anomalous region and 0 otherwise. We operate in unsupervised settings, which means that we assume that the training set only contains normal images, so we will not see any anomaly during training. Our solution consists of an autoencoder, which is quite standard in anomaly detection. And for those of you who are not familiar with autoencoders, they are deep neural networks consisting of two parts. The first is an encoder that extracts from the image a compact latent representation. And then there is a second part, second neural network, which is called the decoder, that reconstructs an image from the latent representation of the same size as the input. These two networks are trained jointly to, so that the reconstructed image is as similar as possible to the original image. So the rationale behind this solution for anomaly detection is that since the autoencoder will be trained only on normal images, it will not be able to reconstruct correctly the anomalous regions, and so we'll see a difference between the two. During testing, the pixel-wise difference between the original and the reconstructed images can be used to produce an anomaly score, which will help us identify the anomalous regions. Traditionally, autoencoders are trained to minimize the mean square difference between the original and the reconstructed image, and so the loss is called the mean squared reconstruction error. However, this metric only takes into account differences in the values of individual pixels and neglects any other information that characterizes the structure of the texture. And this, we will see in our experiment, will result in poor anomaly detection performance. We propose to train the autoencoder using a different loss function, and in particular a custom loss function based on complex wavelet structural similarity, which is the weird acronym you saw in the title of the paper. And this is a structural similarity metric that can effectively capture the most important characteristics of the texture. And so these kind of metrics are much better suited than the mean squared error to do anomaly detection in texture images. This metric is based on the so-called steerable filter decomposition, which takes an input patch as input, and applies a convolutional kernel. So this is the output of the first convolutional kernel, then performs a subsampling, applies again a convolutional kernel, and so on. And this procedure is repeated for several of these convolutional kernels with different orientations, so to extract all the edges, all the important features of the texture. And this results in having a certain number of subbands, which we indicate by XM. And then these subbands are divided into smaller non-overlapping patches, so that to extract all the local information. So the same, given an input patch X and the reconstructed patch Y, the steerable filter decomposition is applied to both of them, and then the loss function will be computed with this formula, which is basically the average of the inner product between the input and the output smaller windows, normalized by their squared norm, plus a constant to prevent the denominator from going to 0. In our experiments, we test our solution on two different well-known benchmarks. The first is the Nanofiber dataset, where we have these grayscale images acquired by a scanning electron microscope of this nanofibrous material, which might have some anomalies of this kind. And we also test on the MVTech texture dataset, where we have some textures taken from everyday objects, like a carpet or a leather surface. So we will have a wide variety of textures and a wide variety of possible anomalies. Let's start from the results on the Nanofiber dataset. Here we measured the anomaly detection performance by the AUC, which is quite standard, and we also use the defect coverage, which is basically the median proportion of the recognized anomalous regions when setting the false positive rate at 5%. We can see that our solution, which is the last one over here, outperforms both traditional machine learning baseline, which is based on sparse representation, and the current state-of-the-art on this dataset, which is this feature dictionary method in which a pre-trained convolutional neural network is used to extract features from the input patches. The second thing we can observe is that we have trained the same autoencoder with different loss function, starting from the mean squared error and other structural similarity metrics, and we can see that the mean squared error performs quite poorly, while the structural similarity metrics perform much better. Let's see the results on the other dataset. Here we have only the AUC, and we computed on the different textures at hand. We can see a similar result as before. So we have that our solution outperforms both the feature dictionary method, which we have seen before, and also the current state-of-the-art on this dataset, which is the student-teacher method, which is also based on pre-trained convolutional neural networks. And it outperforms it on 3 out of the 5 considered textures. And again, we can see that our autoencoder is the best among the other autoencoders we have tested, which perform quite poorly. So yes, this is more or less the results. If we look only on the autoencoders, we can see that the anomaly detection performance strongly depends on the capability of reconstructing the the normal parts of the image. So we can see that if we train the autoencoder using the mean squared error, we have a quite poor reconstruction, and especially on the edges of these nanofibers. And we can see that this makes it almost impossible to distinguish the normal parts of the image from the anomaly. We can see that using the structural similarity metrics, the reconstruction of the reconstruction quality improves, even though we have still some small artifacts in these cases, which I don't know if you can see. Okay, and we can see that using the complex wavelet structural similarity yields the best quality of reconstruction and also the best anomaly score. The main limitation of our work is that complex wavelet structural similarity is designed to process only grayscale images, and of course, colors might be very important information because I don't know, some anomaly might consist in a change of color in a particular region of the image, which of course our method would not be able to detect. For this reason, we are working on including color information in our loss function. But still it performs quite well so far. So just as a conclusion, I think the take-home message of our work is that a simple autoencoder trained by an appropriate loss function can effectively detect anomalous region in textures, and in particular using complex wavelet structural similarity substantially improves the detection performance compared to the mean squared error. And the second message is that this very simple solution can outperform the state-of-the-art, which is usually composed of much more sophisticated architecture, and this we have observed this in different contexts. So that's it. Thank you very much.
Thank you. Questions, please? So
loss basically includes the ability to reconstruct the image, and so when you have an anomaly, you detect it more easily. Did you compare this with using adversarial losses, so to further improve the reconstruction quality, and do you have an idea of what would happen in that case?
Actually, we haven't tested any adversarial losses, but we have seen that there are some methods based on GANs that try to do similar anomaly detection problem. However, in our work, we have tried to keep the architectures as simple as possible. And so in this particular case, we have tested only the autoencoders and the other methods based on pre-trained networks.
Okay, thank you.
Other questions? Comments? Yeah.
So, hello. I'm not sure, maybe I missed it. Do you still need the threshold to determine if there is an abnormality or not, right?
Yes, of course.
How do you find this threshold?
Yeah, actually, in most of our experiments, we have only measured the AUC. So in this case, you really don't need the threshold. But if you would, you would measure the anomaly score, which is made by which is the same metric used as a loss function for each pixel, and then you would set a threshold setting, for instance, the false positive rate to a certain number. Okay, yes, on individual pixels, I say yes.
Okay. Thank you very much.
Thank you.
I think we can stop here and go to the. Let's thank the authors again.
Thank you.
Let's go to the second talk, which is titled LDD, a dataset for grape disease object detection and distance segmentation by Leonardo Rossi, Marco Valentis, Sara Elisabetta Legler, and Andrea Prati from University of Parma and Horta SRL. And the talk will be given by Leonardo Rossi, right? Yeah.
Okay, welcome to this presentation about our datasets. So this is a special challenging use case for object detection and segmentation, and we will see later why I say that. So I come from IMPLAB in Parma, in Italy. So I actually finished my PhD last week. So I'm working usually on object detection and segmentation, but now we'll work on video for anomaly detection on videos. So if you have questions, we can contact me with this email. So first, I will introduce something about the dataset. So usually, what we wanted is to recognize the diseases on the plant. In this case, the grapevines. So we wanted a system that is you can recognize easily and smartly, and maybe it's better if it's distributed. So usually it is done by an expert that visual check the plant and see which diseases is affecting it and how much is extended. But this could be done by an AI. That's why we tried to use artificial intelligence for doing this job. And it's more easily and cost less, and you can use it directly from the user without needing an expert on place. So this project was born in collaboration with Horta that is a spin-off from University of Cattolica. And they asked us an application that is used by inexperienced users, so people that have some grape wines at home and can use their phone to check and with making a photo and returning some statistics about which type of the diseases they are affecting them and how much is extended and also for some more advanced statistics. Usually they only offer some application for DSS and for offering a web interface to make some alert, but now they want to give some instrument, something that can be used directly on the field from users. So for that we collected more than 1,000 images and taken from a natural context because we wanted to emulate the scenario, the worst scenario where people use their phone and can include apart from the plants, can include any kind of objects and any kind of the diseases. So we annotated with more than 70,000 annotations. We used the COCO-like formats because it's quite standard for literature for this kind of tasks. And we labeled with the grape, the leaf, but also plus 8 different diseases. And we already split for the training and on the validation. So we used the software Label Studio to make the labeling, and we needed because sometimes it can be difficult also from expert people to recognize the diseases. We need multiple steps for validating the labels to have a robust data set for training. So these are the classes of the data sets, and you can see the number of instances for each categories, and you can see that it's quite an imbalanced data set because some diseases are more difficult to have some examples. But the good thing is that the same distribution you have in the training, also in the validation. So in these plots, we have a number of categories for images, but also we showed also the number of instances. Typically, the typical use case that is people that make a photo of on the leaf or the grape, and you have usually 1 or 2 categories for images, but the number of annotation in the single images can reach also more than 100 annotations. And that's why, because typically the diseases is distributed and they have in irregular shape. So it's quite a hard job to label them and put all. Here we can show the annotation size respect to the size of the images. I split it into plots for the grapes and leaf, and the others in the right for the diseases. And you can see that there are very different distribution, where the grapes and leaves have a more equal distribution, all the size, but the diseases usually typically is very, very small. And the number of the annotation compared to the leaf is really big, and you can see that typically more than 80% of them are really, really small. So it's quite challenging for the object detector and the segmentation model to find all. So here we tried some models have a baseline. We tested the well-known masked CNN models, but we also tested our models called the R3 CNN. That is something that is taking the advantage of cascade architectures, but with the same size, the same components of the original masked CNN. And on the bottom, you can see the performance. And as expected, the most difficult job is to distinguish the background from the diseases. And that's what we expected because we try to take a photo from a natural context. So simulating the use case of people that are making photo. So here we can see some examples on the left from the ground truth, and from the right are the classification and segmentation from the models. You can see that the models already have a good performance. You can have encouraging results. But it's more difficult part to find the not confounded with the background, I said before. So for the conclusion, we collected a quite a small data set because only 1,000 images is not too much, but it's a hard job because the diseases they are really distributed and difficult to segment, to annotate them. But as you can I showed before, the performance is not so bad, but they still need to increase a lot and we need to integrate them also in production. And because the models are quite big for a phone, we have to find a solution for using some cloud application because we still not. The instant segmentation is is difficult to have a model really small that can be executed online on phone. So we will extend the data set also for other diseases because there are a lot more that we excluded for now. So that's all for my side. So thanks for listening. And if you have questions.
Thank you. Some questions? Comments from the audience? No questions? Yeah, one question there.
Hi. Just a little curiosity, perhaps I missed it during your presentation. I was wondering if your system is robust against the species variation. As you know, in Italy we have different grape variations. In Sardinia we are famous for Canonau here, for Negramaro. So I was wondering if your system is able to classify diseases also with such issues.
Well, we didn't add the class for each variation because it's not needed in our case. But we tried to have quite image directly to the grape or the leaves. So for the models, I think it's quite efficient for this case, less problem, and I think well we still have a few images to test if it's working also for all the type of the grapes, but I think this will be it's not the real problem for this kind of application.
So it's a single grape dataset.
Yeah, you have different images coming from another data set, but also from internal database of the Horta spin-off, also from images taken from us directly.
But the diseases are classified, so it's also the goal of the dataset to present several diseases? Or?
Yeah, we have to distinguish which diseases and also how much is spread to the leaf of the grape. So I offer all the statistics built on
one
top.
disease only?
No, we selected eight different diseases,
okay, 8.
but we wanted to increase the number of them.
Okay. Sorry, I just touched to your question. Other questions? Just a curiosity also from myself. I noticed maybe from the plots that the validation samples are sometimes more than the training samples. Any particular reasons? So usually you consider more samples for training and less for testing.
Yeah, you split it in 80% and 20%. What I showed.
Yeah, maybe I missed something. Okay.
Is a percentage.
Yeah, because I see train is lower than validation.
Because this one is a percentage to the total size of the.
Okay. Anyway, yeah, I mislead something. Okay, so if I have other question, yes, one question here.
I was wondering if you could say a little bit more about the methodology used for the human annotation and if you used iterations of the models in order to improve the human annotation.
So we needed we used the Label Studio software for making the annotation, and we needed more than one step to be sure that the label is correct, because sometimes it's not easy to sometimes in the early stage of the disease it's difficult to understand which one it is. So.
Were you able to use like earlier iterations of the model to catch discrepancies between like human annotations? Like if two of the experts disagreed?
We use only humans for the labeling them, yeah. Because for us it was more easy.
Thank you.
Thanks.
Okay.
Thanks for the question.
So thanks, and let's thank the author again. Okay, so the third paper is titled Mobdrones, a drone video dataset for man overboard rescue, still a dataset. And this is given by Davide Caffarelli, Luca Ciampi, Lucia Valdicano, Claudio Gennaro, Andrea Berton, and a lot of other people, let's say. And the talk will be given by Luca Ciampi.
Good morning. I'm Luca Ciampi from the Institute of Information Science and Technologies of the CNR of Pisa. Thank you for the opportunity to present our work, Mobdrone, a drone video dataset for man overboard rescue, in collaboration with Donato Caffarelli, Lucia Vadicamo, Claudio Gennaro, and Fabrizio Falchi from the same institute, Andrea Berton from the Institute of Geosciences and Earth Resources, and Marco Paterni, Chiara Benvenuti, and Mirko Passera from the Institute of Clinical Physiology of the CNR of Pisa. So in this talk, I will introduce the Mobdrone Dataset, that is a large-scale drone view collection of images that is suitable for detecting persons overboard. First of all, I will motivate and I will describe the considered scenario, and then I will describe the collected data. Then I will show you a performance analysis that we did exploiting several state-of-the-art object detectors and using these new data. So in 2021, the annual overview of marine casualties report that between 2014 and 2020, in the waters of Europe, more than 500 people dead, falling in water during marine casualties. So quick and effective search and rescue operations are crucial. And in particular, it is essential to determine a limited search area for rescue boats. One solution can be to use drones equipped with a video camera, for example, and artificial intelligence techniques in order to search for people overboard automatically and then speeding up the rescue operations. There are plenty of artificial intelligence techniques in the literature, mainly based on deep learning, that reach the outstanding results in detecting objects in images. However, they suffer from limitations. That is that deep learning algorithms require a huge amount of diverse labeled data for the training phase and also for the performance analysis. And it is not only a matter of quantity of data, but also of quality, in the sense that data should cover the widest number of different scenarios and should be also well labeled, avoiding as much as possible wrong annotations. And there are some public available datasets. For example, there is the Google Images dataset and the Microsoft Coco dataset for object detection. Or there is the Mobdrone Dataset for the object detection in drone views. However, there is a lack of annotated data for object detection in drone views in marine environments. And so, to this end, we collected and publicly released a large-scale dataset of people simulating the need to be rescued in water. Data was gathered from one drone flying at various altitudes above the mean sea level and contains several object classes. And beyond collecting and annotating this data, we also performed an in-depth experimental analysis of the performance of several state-of-the-art object detectors. And we hope that will be served as baselines for future works. So I now describe our dataset, starting from the data collection phase. So about the location, the drone shooting activities has been carried out in the Gombo beach of the Migliarino, San Rossore and Massaciuccoli Park of Pisa. We employed 2 professional divers to simulate various scenarios of a person overboard, and to guarantee variability of data, we identified several dimensions of interest, such as subjects or objects to be filmed, person's state of consciousness, person's visual appearance, different light changes, and different altitude and camera directions. And in total, we collected 66 high-resolution videos gathered from a Phantom 4 Pro version 2 drone, employing a certified pilot of the Flying and Sense service of the CNR of Pisa for the drone flight operations. Then we converted the 66 videos from 4K to 1080p resolution, and we extracted the frames at a rate of 30 frames per second for a total of more than 126,000 of images at 6 different altitudes above the sea level, specifically from 10 to 60 meters. Then an expert annotated all these images with bounding boxes, precisely localizing each instance of the objects of interest. And so it is a dataset suitable for object detection, as I already said. The annotation process took about 60 hours using the computer vision annotation tool. And we considered a total of 5 classes that are person, boat, surfboard, wood, and lifebuoy, for a total of more than 181,000 of annotations, of which more than 130,000 concern the people category that is of primary interest in the mob scenario. These are some samples of our dataset of different camera angles and different altitudes. And I zoomed the bounding boxes regarding the people category for a better visualization. Now I briefly show you the detection performance analysis that we did. In particular, we focused on the detection of the overboard people, that is on the localization of the object instances belonging to the class person. And we exploited the world mob dataset as a test benchmark, but we provided train and test split for future works. We evaluated the several state-of-the-art object detectors. Specifically, we compared 9 of the most popular and performing object detectors that are present in the literature. And then we looked at the best 3 ones performing a more in-depth analysis. And specifically, we divided the detectors into 3 main categories: anchor-based CNN methods, anchor-free CNN methods, and transformer-based methods. All the detectors were pre-trained on the COCO dataset, so there are 80 classes, and we filtered the detections considering only the ones classified as persons. And we used standard metrics basically for the detection task, like, for example, average precision. Here I show you the comparison of the these 9 state-of-the-art detectors in terms of average precision, fixing the IOU at 0.5, and also in terms of mean average precision, varying the IOU from 0.5 to 0.95. And as you can see, in general, all the detectors exhibit moderate performance because it is a very challenging scenario. However, the most performing is Varifocal network, considering both the metrics, followed by Todd and the deformable data. Here I would like to show you instead a comparison of these 3 best detectors at different altitudes. As we expected, the performance decreased with increasing altitude because objects become smaller. However, it is interesting to note that Todd and deformable depth particularly struggle to detect small objects. That is when the altitude is above 40 meters, while instead achieved comparable or even better results than a varifocal network at altitudes below 30 meters. Finally, I would like to show you a class-wise analysis that we performed using the best detector, that is the varifocal network. And in this case, we considered all the detections belonging to all the 80 classes, and we took into account also errors due to misclassified objects. That is, detected objects that matched with person annotations, but that were classified as objects belonging to another category. And as you can see, Varifocal network correctly detected more than 80% of the ground truth person instances, even if in most cases it misclassified them. For example, often persons are detected as birds, and this can suggest that the same model fine-tuned on the mob data may have room for growth in localizing person instances. Finally, I would like to show you just a couple of qualitative outputs of Varifocal network, where I highlighted with different colors false positive, true positive, false negative, and ground truth bounding boxes. And so, to conclude, we presented this Mobdrone benchmark, that is a large-scale drone view dataset that is suitable for detecting person overboard. It is part of the Nausicaa project that aims at creating a control system that uses aerial and marine drones to provide the increased safety to medium and large boats. And to this end, we collected more than 125,000 images, and we manually annotated more than 180,000 objects in a marine environment under several conditions. Then we conducted an in-depth experimental evaluation of several state-of-the-art object detectors, and our analysis showed that detectors pre-trained on the standard dataset of everyday objects like COCO exhibit moderate performance in detecting people at sea. And it seems that the classification stage is the primary source of error for the best of the tested models, that is varifocal network. That's all from my side. We published the dataset on the Zenodo repository, and we also made available all the performance, the code for the performance evaluation GitHub. Thank you very much for your attention.
Thank you. Questions?
Hi, thank you very much for your work and your presentation.
Thank you.
I was just wondering, don't you think that the lack of children in the data set really impairs the practicability of the data set? And also the second question is why you resize the images to such a small size? Thank you.
About the first question, there are no children, so it could be a limit, but we should test also with other data in the future to see if they can be correctly detected. And can you repeat, please, your second question, because
The size of the resolution of the images, if I well understood, right?
why we decrease the resolution?
Yeah.
Yeah, just for a matter of space of storage space.
Do you know how many pixels, like how big the persons were in the end? Like if you're from 60 meters up and you have pictures that small?
We did not measure. We did not measure the pixel of in different altitudes.
So the windows, the detection, the bounding box detection, how large is it? For the smallest one, let's say.
So I should have to see, because I haven't now the exact dimension, but approximately just some pixels, because especially just a few pixels, especially from an altitude of 60 meters, the objects are obviously very, very small. So maybe this is the main challenge for detecting this kind of objects.
Other questions? From there.
Yeah, my question is still related to the practicability of your approach. Indeed, in Italy, I suppose also in other countries, we have some limitation about the use of drones that must fly far from people, and also we have some limitation about the guide of the drones. Indeed, we must keep control, visual contact with the drones. So I was wondering if you encounter some limitation, and how did you manage to handle such limitation?
In fact, we employed a professional driver for the image acquisition. And then, I may agree with you, it could be also limitations in the practicability, because there are some strict rules to be.
Anyway.
I don't know, just to add that they said to us that when you are in international water, far from the border, they can play poker, etc. You can even draw this kind of drones.
In any case, this is done for rescue.
Yes, even
institutional. So I think the drone can be flown.
Yeah.
Can be flown for. I have other questions, maybe from the audience. I just have a quick question. It was about. You, in a way, focus on object detectors, in a way, with kind of several types of objects. But the kind of images you are taking from the top, and it seems like more a problem of anomaly detection. If you in a way, if you don't want to localize other people, of course. So you have a people, but you have also both, you have in a way, Rex, something like that. So did you try, did you think that an anomaly detection approach can be useful as much as object detector?
Yeah, it could be interesting to. Yeah, it could be interesting to. And we plan. Yeah, we planned also something for the future. Also for the detection of the other classes of objects that we did not take into account in this first analysis.
Okay, thank you. So
Thank you
I think we can go on. Let's thank the authors.
Thank you very much.
So next talk is titled Investigating Bidimensional Downsampling in Vision Transformer Models by Paolo Bruno, Roberta Moroso, Marcella Cornia, Silvia Cascianelli, Lorenzo Baraldi, and Rita Cucchiara. And the talk will be given by Roberta Moroso.
Okay. Good morning. I'm Roberta Moroso, a PhD student at the ImageLab research group of the University of Modena and Reggio Emilia in Italy. Today, I'm delighted to present our work entitled Investigating Bidimensional Downsampling in Vision Transformer Models. Our goal is to investigate the application of a bidimensional max pooling operator to improve the efficiency of transformer-based models. So, despite having been initially proposed for natural language processing, transformer-based architecture have recently demonstrated their effectiveness also in many computer vision fields, reaching the state-of-the-art results in several tasks, including image classification. The key feature of the vision transformer, the VUIT architecture, are infinite receptive field, achieved to the computation of content-based pairwise similarities, the ability to learn long-range dependencies, fewer sequential operations that allow network parallelization, a scalable architecture, and better generalization thanks to the absence of inductive biases. But by analyzing the structure of the vision transformer in more detail, the main disadvantage of this architecture immediately emerged, namely the high computational cost. Let's start from the input. So the input image is divided into square input patches. The patches are then projected through a linear layer. We add a positional embedding, and we concatenate a classification token that is finally used to predict the output class. So all the patches plus the classification token goes to the transformer encoder. The transformer encoder consists of L transformer layer. Each transformer layer is made up of a multi-layer perceptron, 2 normalization layers, and a multi-held self-attention layer. The multi-held self-attention layer, in turn, performs the scale.program self-attention function over 8 different sets of keys, queries, and values. The results are then concatenated and projected through a linear layer. The keys, values, and queries are obtained from separate and learned linear projection of the patches, of the embedded patches. So all the patches goes through all the layers of the transformer. So as transformer maintain a full-length sequence across all layers, the overall architecture of a vision transformer features a computational cost that increases with the length of the embedded patches, of the sequence of embedded patches. And while this appeared to be an issue only from a computational point of view, it actually hinders the fact that the transformers lack a hierarchical structure that is specifically designed for images. So to solve this problem, we propose VT2D, a hierarchical VUIT vision transformer with bidimensional max pooling that offers a significant reduction of the visual token sequence length and therefore a reduction of the computational cost associated with the transformer encoder, and a hierarchical structure that allows better localization of features when compared to a traditional one-dimensional max pooling. So let's now take a closer look at our proposed architecture. We start from the input image. As in the original approach, in the original VUIT, we divide the input image in square patches. The patches are then linearly projected to the dimensionality of the model, the embedded sides, and we had a positional embedding. The difference with a traditional approach is that we do not add a classification token. The embedded patches plus the positional embedding goes through a transformer layer, and we obtain a sequence of visual tokens that has the same length as the input until now so far. So now we apply the bidimensional max pooling. Okay, first we rearrange the sequence of tokens to the original spatial configuration. Then we start applying the downsampling, the bidimensional downsampling with the pooling to connect different patches and to reduce the length of the sequence of tokens. The downsampled visual tokens are then added with a set of new learnable positional embeddings, and this result is fed in input through two additional transformer layers. All these stages that I just explained are repeated m times. We had an average pooling layer after the last transformer layer of the last stage of our architecture in order to reduce the length of the sequence to a single token. And this single token is fed in input to the last fully connected layer that predicts the final output class. So with our proposal, we are able to decrease the computational requirements of a transformer-based architecture, and at the same time, we create a hierarchy in the feature extraction process which resembles the one of a convolutional neural network. We additionally investigate the effect of applying the bidimensional max pooling operator at different stages of the proposed architecture. So we propose VT2D1, which is equipped with only one pooling layer, and we study the effects of applying the pooling layer in the first, in the second, in the third, and in the fourth and final stage of our architecture. We will see in the experimental results how the stage of application of the max pooling layer will affect the model performance, both in terms of accuracy and also computational costs. We additionally propose VT2D2, which is equipped with two pooling layers, and we apply the pooling layers in the first and the third stage of our architecture. And finally, we also propose VT2D4, which is equipped with four pooling layers, one pooling layer for each stage of the architecture. Okay, let's now consider the experimental results of this approach, of this bidimensional max pooling. In all our experiments, we follow recent literature on vision transformer architecture, and we devised two different configurations varying the dimensionality of the model, the well-known embedded sides, and the number of attention heads. And we call these configurations tiny and small. In the table, we can see the results of the small configuration of our proposed architecture on the C400 dataset when employing only one pooling layer in different stages of the architecture. Okay, as we can see, pooling low-level features, so executing the bidimensional max pooling in the first layer of our architecture, allows to significantly reduce the computational costs expressed in terms of flops, floating point operation per second, and to reduce the memory footprint, while, on the other hand, applying the max pooling operation in the last layer of the architecture, so pooling high-level feature, will bring a limited reduction of flops and memory footprint and achieves lower performance in terms of accuracy. Also in the table, we can see that our proposed VT2D2 with two pooling layers in the first and third stage of the architecture is able to reduce the computational cost expressed in flops up to 81.2% when compared to the baseline model without pooling, at the cost of a slight reduction of accuracy of about 1 percentage point. We also studied the effects of varying the kernel size of the pooling layer, and we derived that pooling with small kernel size are able to achieve a higher accuracy, but also a higher memory and computational cost when compared with pooling layer with a large kernel size. Finally, our configurations employing 4 pooling layers, one for each stage of our proposed architecture, are able to achieve a reduction of computational cost expressed in terms of flops of about 30%, precisely 28.8% reduction of flops, and at the same time to increase the accuracy of about 2 percentage points. We also investigated and compared the performance in terms of accuracy against the computational cost expressed in terms of flops of our baseline model without pooling in its tiny and small configuration. of VT1D, that is a variation of our architecture where we employ a one-dimensional max pooling, and of our proposed VT2D with 1, 2, and 4 pooling layers. We can notice that our proposed VT2D 4 with 4 pooling layers is the model that achieves the best trade-off between accuracy gain and flops reduction. And we can also notice that the tiny version of our model with only 5.6 million of parameters is able to achieve performance that are comparable to the baseline model without pooling, but in its small configuration, having 21.7 million of parameters. So our model with 4 max pooling layers is able to obtain performance in terms of accuracy that are comparable, but with a reduction of parameters that is about 50 million, and a significant reduction of computational cost in terms of flops. Our results are also confirmed on the ImageNet dataset, that is a much bigger and more complex dataset than CIFAR100. And in particular, our results on ImageNet confirms that pooling layers in early stage is able to improve the accuracy and to reduce the computational cost in terms of flops, while pooling in the last, with small kernel size, are able to improve the accuracy, but at the cost of a higher memory and computational requirements. Okay. As a final analysis, we also report a comparison of our best variants against the state-of-the-art approaches. And in particular, we considered approaches that are based on the vision transformer architecture and that employs some techniques to improve efficiency of the transformer. And we considered the knowledge distillation approach proposing DEIT, two variations of the DEIT that additionally performs pruning to increase the performance that are SCOP and power, and the one-dimensional pooling-based approach proposing HVT. As we can see from the table, our bidimensional max pooling approach is comparable to the considered states-of-the-art methods, both in terms of accuracy, but also in terms of computational requirements reduction. Okay, let's conclude with our findings. So we propose a bidimensional max pooling operator that is able to reduce the length of the patch sequence processed by the vision transformer architecture, and therefore to reduce the computational cost. We enforce a multi-level hierarchical representation on the feature of the input, and we investigated the effect of applying the bidimensional max pooling operator at different stages of the proposed architecture in the tiny and small configuration. We evaluated our proposal on 2 datasets, CIFAR100 and ImageNet, and we have been able to reduce the computational cost up to 81.2% reduction of flops, and at the same time, we have been able to increase the classification accuracy of about 2 percentage points. And with these results and observation, I end my presentation by thanking you very much for your attention.
Thank you for the very clear and presentation. So questions? 1, 2.
Okay, thank you so much for the very nice presentation. I have,
Thank you.
Sorry, I have one question about the evaluation of the reduction in computational cost.
Okay.
Is the flop evaluation just a theoretical one, or do you have also a benchmark on real device deployment? And also, I'm wondering, all of your find out is essentially, from my perspective, and please correct me if I'm wrong, just a fact of scale of the features, because if you apply max pool immediately, it means that you're not interested in seeing the whole picture, you're considering something very specific. Does it change on datasets which are not just the CIFAR100 or ImageNet, let's say a medical dataset where you want rich features? Thank you.
Okay. About the first question, we didn't try to embed this architecture on a device, so we evaluated the computational cost in terms of flops. We just evaluated the operations that are executed during the training and the evaluation of the architecture. And about the second question, we just evaluated 2 datasets. We haven't tried other datasets like medical application, but this could be a nice possible extension of the work, yes.
We have another question here.
So thank you for the nice presentation, for sharing this insight. I have one comment and one question. So the first comment is, you started the presentation saying that the main advantage of transformers is that they have little inductive bias. And then what you're doing is adding, right, inductive bias, because you're saying these are images, we should treat features as images, which is fine to me, but I wonder where's the trade-off of improving results by limiting the ability to learn a solution by itself. But that's just a comment. And the question is, have you had a chance to compare this with multi-scale vision transformers, which do something very similar, but that approach looks like more computationally expensive because you also have convolutions. And here I see just max pooling, which is very nice because you are not adding parameters. Thank you.
Okay, no, we didn't compare our approach with multi-scale transformers. Yes, yeah, as you pointed out, yeah, there are other approaches that use different scales, or they just have, I don't know, a sliding window and they give different portion of the image to the transformer and then reduce the dimensionality by going deep in the architecture. But yes, there are different approaches, but we didn't compare with them. It could be also a nice thing to explore in a future extension of the work, yes.
Okay, thank you. Thank you. Let's thank again the speaker. Let's go to the other talk, which is titled An Anomaly Detection Approach for Plankton Species Discovery by Vito Paolo Pastore, Nimrod Megido, and Simone Bianco, and the talk will be given by Vito Pastore.
Okay, so good morning, everybody. My name is Vito Paolo Pastore, and I am a researcher at the Machine Learning Genova Center in the University of Genova. Today, I will talk about an anomaly detection approach for plankton species discovery, which is a project we have in collaboration with the Center for Cellular Construction and NSF Science Center, including UCSF and IBM Research Almaden. Okay, let me start with a brief introduction. Why is plankton important? Ocean is the first source of protein for 1 billion of people with a fundamental social and economic impact. And also, and plankton is at the basis of the marine food chain. Also, phytoplankton has produced 50 to 70% of our oxygen. So changes in plankton ecology may have rippling effects in global climate, as well as deep social and economic consequences. Unfortunately, we are not taking care of these fundamental microorganisms. And in fact, as we can see here in the top right of the slide, in the last 50 years, due to an increasing of the carbon dioxide concentration and temperature, the phytoplankton population, which here is indirectly measured by using chlorophyll density, has decreased by approximately 50%. Okay, now the question is, why should we study plankton? Now, plankton microorganisms can react to even minimal changes in the environment with morphological and dynamic modifications. If we look here in the right of the slide, we can see an example of a freshwater monocellular plankton, which is called stentor. So in the top images, the stentor is healthy, in particular it is swimming and feeding, while in the bottom it is reacting to a chemical perturbation and it's impaired, so there is a consequent cell shape modification. So same species, but two completely different shape. In this case, it appears clear that maybe we could try and use plankton as biosensor. And how should we do it? An idea is to establish a baseline of both morphological and dynamic let's say, features for the healthy plankton, and then try and screen for significant deviation from such a baseline, which can be associated to a perturbation in the environment or to some modification. In this way, the idea is to monitor plankton population composition and also morphology in this case, and continuously screen for anomaly so that it is possible to preserve, or at least to contribute to preserve, a healthy ecosystem. In this context, we propose an efficient pipeline to provide in situ recognition of plankton species not included in the training set. These plankton species could be an actual unknown species, and this is quite likely because they exist on average 4,000 possible species. Of course, some of them are more concentrated in certain places than others. Or they could be species whose morphology drastically changed because it's reacting to a perturbation, to a change in the salinity, in temperature, or to a chemical. And here in the right of the slide, we can see a toy example. This pipeline that we propose is centered around a custom anomaly detection algorithm that we named the tail detector, simply TDT algorithm. Now I will give more details about the proposed methodology. First, we suppose that a training set is available, an initial training set is available, and this could be either annotated by experts of the field or by means of unsupervised methods. In any case, one TDT anomaly detector is trained for each of the available species and is stored. At this point, the proposed pipeline is composed of three main steps. The first is pre-processing, so the image is acquired, potentially is cropped, is segmented, and then a set of features is extracted. And then I will give you more details about these features in a moment. At this point, the features vector is fed to the TDT detectors that have been trained and that are placed in this parallel architecture that we can see here in the slide. At this point, a sample is considered as a global anomaly if all these detectors reject it, so recognize it as an anomaly, and the global anomaly are stored for further processing. For instance, an idea could be to use a semi-supervised approach for these global anomalies, so that, for instance, you could use an unsupervised or clustering, a partitioning algorithm in order to divide the global anomaly in clusters according to the selected features. At that point, when enough samples are available, an expert of the field could go there and annotate just to understand if those are new classes or are actually cells that are modifying the shape because of perturbation. In this case, if it's a new class, you can simply train a new TDT detectors on that and add it to the collection, as in the stage 2 of our pipeline. So for the pre-processing and for a few details about the features, we follow an approach which is quite, so we design, engineer a set of features which is quite typical of the plankton analysis. In particular, we use 5 different kinds of features, both shape-based and texture-based. For instance, geometric features like the area, the perimeter, the aspect ratio, the Hu and Zernike moments. And for the texture-based, we use hierarchic features, local binary patterns, descriptors of the contour, color features, and features from the gray level histogram. In total, we extract a set of 131 features for each of the plankton images. Now I'll give you more details about the TDT. This algorithm learns, of course, the boundaries of an empirical distribution for each of the extracted features to define a baseline. And this will be the baseline for us of the healthy plankton I was telling about a few slides before. At this point, a bootstrap approach is used in order to estimate the mean value and the standard deviation with an acceptable confidence level. And as one threshold per each feature is defined as the mean value minus or plus a certain n times, parameter n times the standard deviation, with n learned by the algorithm. And the way we learn it is simply allowing that, let's say, approximately 1 minus z% of the training samples are anomaly. In this case, let's say, we have a set of thresholds, so 1 threshold per each feature. And when a sample is tested, we consider it as anomalous if it falls out of the computed boundaries for more than max times, so max features. And max is, again, a parameter learned with the same strategy. In our experiments, for instance, we used 98%, so we are allowing 98% of the samples to be in class and 2% to be anomaly in the training set. On the right of the slide, you can see a pseudocode representation of the training and the testing phase of our algorithm, and more details can be found in the paper. Okay, now we will describe briefly the results. We tested the proposed pipeline on a public collection of 10 species of freshwater plankton, the lensless dataset, which is acquired by means of a lensless microscope. In particular, there are 10 species and 500 images for training and 140 images for testing per each of the species, with a total of 6,400 images. And here in the slide, you can see an example of the 10 species. Okay, so first we test the TDT algorithm and the proposed pipeline on the lensless dataset, and in particular, we of course train on the training set, and then we test with the following protocol. For each of the species, we train and test one TDT algorithm, one TDT detector, and we test the in-class, of course, on the 140 images available, and the anomaly by using the remaining 9 species, so for a total of 1,260 images. We also compare as a benchmark the TDT algorithm with 4 well-established anomaly detection algorithms, which are the one-class SBM, the isolation forest, the robust covariance, and the local outlier factor. And as we can see, the TDT outperforms these benchmarking algorithms on the lensless dataset. We also further compare with an available work about a deep neural network used for anomaly detection on this dataset, which reached the same anomaly detection accuracy and slightly better in-class accuracy. However, the TDT average training time, since the parameter to learn is just the n and max is quite short, is only around 2 or 3 seconds. And so we can conclude that the TDT is still the best compromise trade-off between accuracy and efficiency. Finally, we also tested how accurate is actually the pipeline in detecting an unknown species. And we used the lensless dataset by exploiting a leave one out approach. So every time we remove one of the 10 species and we use the remaining 9 TDT detectors in the parallel architecture that I already described, and it is already in the slide for clarity. And the idea is that the left-out species should be recognized as global anomalies or rejected by the 9 trained detectors. And our performances are around 93%. So 93% of the times, let's say, these samples are actually the left-out species samples are actually recognized as global anomalies. Finally, we can draw some conclusion. So we introduced an efficient pipeline to reveal unknown species of plankton. This pipeline is centered around the TDT algorithm, which outperforms on the lensless dataset 4 well-established anomaly detection algorithms. The implemented pipeline is actually able, with high accuracy, to detect unknown species of dataset. And the idea is that an in situ acquisition system, a microscope, for instance, which is powered with such a pipeline, could provide this continuous screening of the aquatic environment in order to find anomalies that could be related to perturbation or changes in the environment, in this way providing a real-time detection of threats or perturbations. Okay, and with this, I thank you all for the attention.
Thank you. Questions? I suspected there were lots of questions, but no questions. I have some curiosities about your work. So you apply this classical, let's say, feature extraction. You have a lot of features, and you use this approach in which you consider a single class and some, in a way, fitting and thresholds. So this implies that your classes are separable in a way, or not linearly separable.
Not linearly,
but
yeah,
separable in any case.
Yeah.
This is what you find empirically, but I wonder.
So yeah, we are actually now working on more fine-grained plankton datasets which exist, and we are working on the representation part there, so on extracting features by means of, so we just have another paper will be out in few months now about some VIA-based approach for extracting features that are able to distinguish more plankton, which is fine-grained, but we are working on that, yeah. So this is a case in which empirically that depends. If you go to a lake, for instance, this is the situation you have. There are no more than 15 species or 20 species of plankton. Of course, if you go in the sea, and that depends where do you go, the situation is the one of the 4,000 I was depicting, so there you can work on the representation part probably, and then try also to...
Do you plan to use some deep learning features? Because
yes, at this point, yes. Yeah, at that point, yes, like the variation autoencoder extracted features, for instance. We tried something like that, and it seems that works quite well.
Okay, and also consider your approach, since you are in a way checking each feature at a time, right? You see the threshold. Why not using a sort of decision tree which is doing more or less the same?
So I think we tried also with decision trees, but it's in line. It's a little the performances were a little lower. I mean, this could be a potentiality. Yeah, there could be absolutely an idea. Yeah, I mean also that the algorithm works well, but then the pipeline is the main message, probably just how to assemble everything.
Okay, so no question, right, guys? Okay, so one question. There, before leaving the floor to the colleague, you know that there are in deep learning now this open set recognition, which is actually just doing what you are searching for. So just looking. You can have a check at this literature.
Yeah, thank you.
Please.
Yeah, thank you for your talk.
Thank you.
I guess there is also an Italian team working on microfluidics, and they pass plankton through holographic reconstruction. So they get 3D information about the plankton shape. Did you try your kind of algorithm to 3D?
So yeah, thank you for the question. So actually for this data set, we didn't have the 3D information, though this lensless microscope is a particular one in which you have a projection on 2D, but you can actually see because there is no lens. So in a way, you can embed more information. We have a data set which is, we had a data set about holographic microscope where the 2D information was available, but I don't have it yet for analyzing, for processing. So it's a very interesting question, but right now I don't have the possibility to reply. We will try it, yeah.
Okay, so thanks again.
Yeah, thank you.
Okay, last talk, which is actually remote, so please arrange the setup, which is towards a system for post-earthquake safety evaluation of masonry building by Giovanni Giacco, Giulio Mariniello, Stefano Marrone, Domenico Asprone, and Carlo Sansone. And the talk will be given by Stefano Marrone remotely.
Hello. I hope you can hear me.
Okay, ciao Stefano. Okay. Yeah, we can hear you.
Great. I will share my screen, so if you can confirm, you can see my screen in presentation mode.
We see a cat.
Yeah,
now,
it's my background.
Now the slides.
It's amazing.
Okay.
Thanks.
Go on.
So
Thank you. Yeah.
Thank you for your kind introduction. And yes, my name is Stefano. I'm from the University of Naples, Federico II, and I'm presenting you our recent work about the post-seismic evaluation of damages. So this is a brief agenda of what we are going to see. And I want to start by introducing the team who is working on this project, because actually, as you can imagine, this is a complex project as it regards not only image processing, but also a deep understanding about buildings and structures and damages after an earthquake. So this work has been done together by two departments of the University of Naples, Federico II. So the reason behind this paper is that a quick and reliable assessment of structures and infrastructure is crucial for emergency management. In particular, when the rescue operations are over, rapid assessment of damages is mandatory before allowing access to the people living inside those buildings. This evaluation is currently made by human based on visual inspection in order to meet the very highly demanding requirement expected by the regulation board. Despite very accurate, this procedure is, as you can imagine, extremely time-consuming and requires experienced and highly specialized technicians. Since 1997, in Italy, the assessment report document is used as the name of ADAS. And in English, these acronyms should sound like practicability and damage in the seismic emergency. This document that you can see here in the right side of the slide is a form for the fast detection of damages, the definition of prompt intervention measures, and evaluation of post-seismic probability of buildings with ordinary structural topology, for example, the masonry, reinforced concrete, and so on. Similar forms actually are also used in other countries, like, for example, North America and New Zealand. In this context, what we do is to propose the use of vision-based system to support the post-disaster building safety evaluation, and in particular to speed up the process of filling this form. In particular, we introduced the use of support-based of a system based on support decision system, and in particular machine learning, in order to reduce the error when filling this document. What we propose is a system based on image analysis, as I was saying, using a set of pictures of the building to be assessed that provides a synthetic tool to support the compilation and validation of the safety assessment forward. Figure shows a diagram of the overall approach we proposed actually. This approach is based on interaction of two different vision-based predictive models that have the objective of detect, localize, and quantify the damage. Starting from the detecting the openings, the piers and the spreaders and the rigid zones will be identified, followed by the definition and the detection of the cracks for each of these portions of the building. Detecting the portion of the building is extremely important because, as you can imagine, based on where the crack is located on a building, the consequences may be more or less severe. The result of the two components is then synthesized in the matrix of the damages, the one in the top of the slide. This matrix provides information on the amount, intensity, and the location of the damage. In particular, as you can imagine, there is no data set available for this problem. So the first part of our work was to collect as data set. And in particular, as this work aims at being used with different sources, so for example, images acquired by using a camera or a drone and so on, and in particular, we want to make our system being able to work in conditions where the images are very, very heterogeneous, for example, in terms of brightness, shot angles, background, and so on. Thus, to collect a very generic data set, we decided to use both real images coming from post-seismic situation, most of them collected in Aquila, a city in Italy, and also in order to also emulate and simulate the scenario of images coming from the non-damaged building acquired from very different tools and cameras, we collected images coming from the Google Maps and Street View facility. In this slide, we sum up the total number of images, crack, and so on. In this research, different state-of-the-art convolutional neural networks pre-trained on ImageNet were examined for their effectiveness in classifying images from building surface on patch level. This is important, and we will see this detail after. To, in particular, address the problem, we consider it as a multi-class classification, where the model must discriminate between non-crack, low-severity crack, moderate severity crack, and high-severity crack. As the reference is relatively small to enable a robust training of a complete deep learning model from scratches, in this work we leverage transfer learning via fine-tuning. In particular, to find the optimal value for learning rate, we made use of the learning rate range test, that is a sort of technique coming from the AutoML scenario that allows to tune the ML, the learning rate based on the detection rate. The performance of the network was evaluated based on the values accuracy and FS score for the crack classification, while we leveraged the dice coefficient to evaluate the building opening segmentation. Results show that also changing the backbone network for the UNet, the use of the ResNet34 results to be the most effective for both tasks. The reported figure shows how the interaction between the zone labeling and the crack detection provide the final output of the proposed approach. The damage assessment matrix here in the bottom side of the slide provides a quick overview of what is going on, of what our system detected. And in particular, it highlights the location of the parts, the spindle, and so on. Technicians then can use this form to easily fill the information required by the assessment form. Summing up, in this work, we introduced a tool to support the rapid and accurate analysis of data collected by field engineering during emergency operation and reconstruction plans in post-earthquake scenarios. Despite the results are very promising, the system has some constraints related to the characterization of the cracks discovered on the building surface. In particular, the proposed approach was founded on a patch-based crack detection strategy. And as you can imagine, detecting the crack on patches, only based on patches, can limit the effectiveness of the proposed approach. Thus, in future works, we will focus on the semantic segmentation of cracks. Also, we will develop a new module for the automatic filling of the forms. Thank you for your attention. Have you any questions besides those that you are going to ask me? Feel free to get in touch with me by using the email address you can see here in this slide. I'm interrupting the screen sharing just for replying to the question, if any.
I don't know how we can manage the questions. I think it still will microphone.
I can hear you from the room, actually. I can hear quite well because I think the microphone in the room is connected to the internet connection, so I can hear you.
Okay, thank you. Questions? No questions? Wally.
Hi, thanks for the presentation. I was just wondering, you mentioned that you trained, you used normal images from Google Maps dataset for training. So I was wondering, did you need any domain adaptation strategy? Because I guess images acquired with different types of cameras, different distances, different size, and resolution. So was there any problem with that, or could you just use those images as they were?
Thank you for the very nice question. Well, this is a very important point. As I said, our aim is to develop a system that is able to work also with images coming from different sources. So in our case, actually, it turned out that there is no need for domain adaptation. Just to be a little bit more accurate in my description, with Google Maps, actually, I refer to Google Street View. So images acquired by the Google car driving through the streets. So they are very, very similar to the images that can be acquired by using a smartphone or a drone camera and so on. Maybe this is the reason why we didn't need a domain adaptation strategy, but of course, in the future, we will strongly focus on this aspect if the problem will arise.
Other questions? So your images are all from a Google Street View, not you are taking from drones, or you are taking from drones. You said also something related to the acquisition, right? So that's that's a typical for domain adaptation in the sense that if you're taking from the ground and they are taking from the top, so probably there is a problem domain adaptation in there. But we have another question.
Yes, indeed. Also continuing on these Google Street View images, did they also contain cracks, or these were the? But then how can you make sure that, because if you recognize it's not from if it's coming from a random camera, then there is no crack, and if it's a high detail. Yeah.
Absolutely. This is a totally nice question, but let me be let me be a little bit more accurate about this aspect. The problem has two different submodules. One is to detect the building within a scene and to detect the openings like door, window, and so on. And the other one is to detect the cracks on the building surface. So for the first task, detecting the building, the openings, and so on, we used both images coming from Street View and so without any cracks on it because they are not actually needed, and images coming from the camera took on the on situ after an earthquake. The aim here is just to identify damaged and not damaged building from the background. So it's only to detect the building. Then after a building has been detected, we run another module to perform the crack detection. Crack detection has been trained only on images containing cracks, clearly. I hope I cleared your idea about the approach.
Seems so. Other questions? Just one quick question? No? Okay, so let's thank Stefano again. Thank you.
Thank you.
So this talk concludes the session, and thanks for attending. Thanks to the speakers, and see you this afternoon. I don't know if there are announcements from the organizers. No? So have a good lunch.
Sento un po' di eco dalla sala.
Ok, Stefano, puoi partire?
Ok, un attimo solo che mi sento malissimo.
C'è una cosa online adesso?
Ok, perfetto. Ok, perfetto. Salve a tutti, benvenuti alla prima edizione di questa challenge. Voglio condividere le slide così magari utilizziamo queste come sfondo invece della mia faccia.
Scusami, in English, please.
Oh, absolutely. I'm sorry for this. Sorry for this. Welcome to everyone. Let me share my screen so that you can use the slide as background for this presentation instead of my face. Just. Okay, can you see the screen, right?
Okay. Now it's okay.
Great. Thank you for joining this first edition of the AI KFM Challenge. This is the first time we run this competition, and we are very, very happy to have the opportunity to be hosted by ICAIP, and we are very, very excited about all the participants and the results obtained. So before starting, let me introduce a little bit what a KFM is and why we decided to run this competition. Okay. Well, gazing ruminants that are all the animal like cows, sheep, and so on are very, very exposed to parasites. And in particular, the diffusion and spread of parasites may be extremely dangerous also for humans. Over the years, as you can see from this picture, researchers started to develop more accurate tools to detect parasites in fecal eggs. And in particular, they are working on both devices, and with the devices I mean, for example, a microscope, and also on techniques for the automatic detection of parasite eggs within the floating samples. Nowadays, there are a lot of devices. For example, the ones here on the right side of the screen. I'm not sure you can see my pointer actually. On the right side of the screen. And they can be used for different animals, including cattle, sheep, goats, and also humans. In Naples, we developed what is called the FlowTAC and Mini FlowTAC, these two devices on the left side of the screen. They are very recent and new devices that are extremely more effective than those already available on the markets, because they solve some of the problems that is affecting the other competitors. And in particular, these two devices are able to spread the sample over all the acquisition surface. So it's possible to be more accurate and fast at the same time. To analyze the FlowTAC and the Mini FlowTAC, we designed the KFM. The acronym stands for Cubic FlowTAC Microscope, and is a very compact and low-cost portable digital microscope designed to autonomously analyze the sample within a FlowTAC or Mini FlowTAC. In particular, when compared to a standard microscope like the optical one, the advantages of using the KFM is in the use of very fast system that can be used on site. So there is no need to acquire the sample and to bring it at home to the research laboratory, but it's possible to do it on site, so in a farm, for example. Also, the KFM is totally accessible by using an online tool. So you can connect to the microscope by using a remote web app, by using a laptop, or by using a normal smartphone, Android or iOS. One of the advantages, as I was saying, is that it's compact and very, very effective. How can we say that it's effective? Well, we compared it against the results that can be obtained by using an optical microscope. OM stands for optical microscope. And as you can see, the results, the number of detected parasites is almost the same. I mean, by using the optical microscope, it's possible to detect just 2 more eggs when using the KFM. So we are saying that there is no statistical difference between the automatic detection made by the KFM and the manual one made by using an optical microscope. The aim of this challenge, and we decided to run this challenge to make a further step toward the automatic detection by using artificial intelligence. So the aim of this challenge was to perform the detection of fecal egg in images acquired by using the KFM. In this edition that I was saying, it's the first one, we used 11 different acquisition, and with acquisition I refer to different samples, so different flow tag and mini flow tag, and each sample provides almost a little bit more than 200 images each. Of these 11 acquisitions, 7 were used for the training, and the remaining 4 were used for the final test set. And in particular, the test set was divided into 2 stages. Starting from the very beginning, we released just 1 sample for the test set as we ran the challenge on Kaggle, and just 4 days before the final deadline, we released also the other 3 samples to run the final and actual test evaluation. 3 teams joined the challenge, 2 from Italy and 1 from India. And in total, we had almost 15 submissions for this challenge. I know that these are small numbers when compared to very famous competition, but as this was the first time, we are very happy with this. In particular, for the challenge, we had 2 different tracks. The first one, track 1, was only focused on the detection of eggs, while the second track was also taking into account the computational power required to perform that detection. For both tracks, we asked it to share the code in order to make sure that it was possible to reproduce the obtained results, as in this case, the data was focused on animal production. Results showed that detecting these eggs is not trivial, and that's the reason why we still want to push towards the definition of automatic detection tool for fecal eggs detection. And the winner of this first year competition, was the Parasite team from Sardinia. And the score is reported here. I want to pay attention to the fact that these scores are a little bit different from the one available on Kaggle, as Kaggle did not update the leaderboard after the release of the new dataset. So these are the scores that can be obtained by using the host facility. Finally, the Parasite team also shared the code for running the track 2, and in this case, they were able to elaborate almost an image per second, making the proposed approach possible to be used in a real clinical context, clinical scenario. Despite the fact that there is only 1 winner, we open the chance to all the participants to contribute to a paper we are writing for describing this first challenge, and so all the participants are invited to submit a brief description of what they did to achieve the results they present, and in particular, the Parasite team is going to present. I don't want to take any time further from the winner, so I will stop sharing the screen and give the floor to the, I think, Professor Marchalis, who is leading the Parasite team. That I think is there in presence, right? Am I right? Can you hear me? Can you confirm?
Can you hear us?
Yep.
And me, Stefano, Gianluca speaking.
Yes. Yeah. Okay. I confirm.
Okay. In order to see the screen presentation. Okay, thank you, Stefano, for this opportunity to test our abilities in designing deep learning approaches to recognize parasites in ruminants. This is actually the composition of the lab. Is a large laboratory made up of 10 people, but for this specific challenge, only 2 people specifically devoted their time to design an appropriate method for parasites classifications. I just 2 words about our main research activities. We work on biometrics, and so we develop features and systems to recognize human people. We also have an important asset in biometric anti-spoofing, especially fingerprints, where we gained a large experience in fabricating spoofed fingers, and also we are the organizers of the International Fingerprint Liveness Detection Competition. Last but not least, we also work in anomaly detection in crowd, thanks to a project recently funded on the theme of Boolean action recognition. Okay, the problem was already fully explained by Stefano, so I simply move to the solutions proposed by the parasite group made up of Giulia Orru and Luca Ghiani, who gives his help from University of Sassari. Okay, the main architecture is explained in this slide. We started from an existing architecture already released at the link you can see below, and for improving and specializing this network, firstly, we performed a fine-tuning phase, fine-tuning stage, and then we corrected the decision of the network, which was not designed to parasite classification, by an appropriate post-processing module. We described, in particular, the pattern of each parasite by a geometrical point of view. By using this very simple approach of description, we removed a lot of false positives performed by the network. In this slide, I just summarize the approach followed by the parasite team, and as you can see, they described very specifically each part of potential parasite detected by the network. In this case, the parasite group has been able to improve definitely the performance, and in this slide I show the 2 steps. First step, classification performed by the neural network with fine-tuning, and the second step, the post-processing approach. The other details are referred to networks change from a model to another one, but nothing is very, very relevant. The most important thing is that this experience allowed us to highlight the importance of post-processing in pattern classification. In many cases, we still see classification performed only by neural networks. We are very happy to perform, to carry out an improvement of the classification rate by a simple geometrical traditional approach to describe patterns. So we can see the two scores that already our Stefano reported in his slide, but in this slide I also added some more results from other models we used in this case. The last model is YOLOV 5, but the most of the merit in this recognition rate was done by the post-processing phase. Okay. F1 match scores over the confidence and the precision recall curve, which are very good by considering that this was our first experience in this task. Okay, conclusions. Fine-tuning is important. We can already use existing networks for other tasks, as for example, pedestrian detection and so on, but it is not enough, because these gastrointestinal parasites exhibit a very peculiar shape, and this shape can be pointed out by an appropriate post-processing phase. Okay, thank you very much, Stefano. Thank you all for allowing us to describe our joint work, Giulia and Luca from Cagliari and Sassari, respectively. Thank you once again, and thank you, Cosimo, for hosting us at this conference.
Thank you, Gianluca. Stefano, would you like to?
Absolutely. Yes, thank you for the very nice presentation. And I have to say that your idea is absolutely correct. I mean, post-processing is absolutely crucial in this context, and I think you did a very, very good job. For example, we on purpose made this challenge a little bit difficult because the round objects that are present in images are just airball. They may look similar for an automatic detection system, but they are very trivial to be recognized by a human operator. So the aim of this challenge for the first year was to raise attention on the fact that actually, as you said, it's important to design an ad hoc procedure to understand whether it was actually an egg or something else. We are already working on the second year edition of this competition, and we will make things a little bit harder by introducing other parasites that look similar to egg ball. So I hope you will join also the second year, and I'm looking forward to receiving the 2 pages description of your work, and I think we can make together a great work out of this experience.
Okay, thank you, Stefano, for your kind words.
Thank you again for your presentation. Thank you again for the hosting facility. Thank you all. And this ends the presentation for the AI KFM challenge. Thank you all again, and hope to see you soon in the next future.
Thank you. Bye, Stefano.
Bye-bye.